Hi everyone, my name is SwarmOptimization and I am currently pursuing my PhD in computer science under the guidance of Dr. Nami from Texas Tech University in Lubbock, Texas. I will now be talking about my topic on vulnerability coverage for adequacy security testing, which got selected as a poster in SAC. As we're all aware that almost all software applications are embedded with great number of configuration settings, which can be tweaked according to user's preference in order to get desired functionality. Oftentimes, due to improper settings of the configuration parameters by user, it leads to a vulnerability that the attacker can exploit. According to NVD, as of September 2019, there have been nearly 1600 records of reported vulnerabilities with assigned CVE numbers. CV basically provides unique identifiers to known security threats. The concept of our paper is to introduce vulnerability coverage as an advocacy criterion for choosing instances of vulnerabilities that the software under test needs to be checked against. And we utilize CVSS as a means to measure the severity of the vulnerability in software under test. Here's an example of a CVID which was released in 2019 for the MySQL product, whose CVSS score was 8.2 and severity was high. As mentioned before, the objective of our research is to introduce vulnerability coverage as an advocacy criterion for testing systems and their configurations. For this, we adapted GEO and PSO to generate advocate test inputs with respect to the introduced vulnerability coverage criterion. In the end, we reported the performance of the proposed technique through a case study demonstrating the feasibility of the proposed coverage criterion. Now we'll talk about Common VulnerabilityScoring System. It is basically a way to capture the principal characteristics of a vulnerability and produces a normal score which reflects its severity. This score ranges from 0 to 10, 0 being the most secure in the ideal situation, and 10 being the least secure or of higher severity. It is composed of three main metric groups: base, temporal, and environmental, and each of these have their own set of sub-metrics. But with this paper, we'll be only dealing with base metric, as it reflects the severity of a vulnerability according to its intrinsic characteristics, which remain constant over time. On the right, you can see the how sub-metric group is divided into two main how the base metric group is divided into two main sub-metrics: exploitability and impact, and each of them have their own corresponding vector fields. Scope is a vector field which does not fall into these two sub-metrics. If you want to read more about other metrics in CVSS, you can go to the CVSS official website. I'll provide the link down below. Let's talk about exploitability matrix. It describes the how part of that that is being captured. These are the four fields that belong to this metric: attack vector, attack complexity, privileges required, and user interaction. And the second column provides a description for it. What the main thing to notice is the values that each of these field takes. For example, in attack vector, it takes four values: N, E, L, P, where N indicates that the attacker can attack remotely from network, which is considered to be easy from attacker's point of view. Whereas in case of P, it means that physical presence of the attacker is required, which indicating it's hard to attack. So and so forth. For attack complexity, if it's low, it's easy for the attacker. If it's high, it's complicated for the attacker. And the same goes for privileges required and user interactions. Now let's talk about impact matrix. It reflects the characteristics of the impact components. It again takes three fields: availability, integrity, confidentiality. And all of these fields take the same values: none, high, low. Here again, if the value is none, that means none of the component was impacted. If it's high, then severity was high here.
About the scope matrix, it's a different field which does not belong to any of these two submatrix. It describes the scope of the attack, where scope indicates whether the vulnerability in an application impacts resources beyond its means, and it takes two values, unchanged and changed.
This is an example of a vulnerability found in the NVD website. It has the CVE ID 10665. This is the current description about the CVE. And if you see down below, we have two versions of CVSS metrics. One is version 3 and version 2. But version 2 has become obsolete, so we'll only focus on the version 3. As you see, it has a corresponding CVSS string or pattern corresponding to this CVE, and the base score has been and the base score is 9.8 for this vulnerability, which has the vector pattern as mentioned here. And since it's 9.8, it's deemed as very critical because the maximum value for this vector can be 10. Hence, 9.8 is critical. Also know that the value of this base score depends on what values these vector fields take. So they have a huge role in deciding the score for the deciding the base score for the vector. Now I'll talk about the methodology. Here the aim is to generate vulnerability or CVSS pattern, one and the same thing, targeting certain ranges of CVSS score. We use GA and PSO as optimization algorithms. CVSS score is used as a fitness function. And in GA we developed a Python-based script that generated secure CVSS vector string pool, where the initial pool was insecure and through iterations it generated a secure pool of strings. We kept the fitness score range between 2 to 5, kept the iterations to be 50, population size 100, and we utilized a package in Python called CVSS3, which calculates the base metric score of a CVSS pattern. And for selection, we use the Breeder's selection and 1-point crossover, and we kept the mutation rate at 0.5. For PSO, the implementation was somewhat similar to GA, but there was no crossover mutation as such. We kept the number of iterations and population size same as GA to maintain the consistency. And in PSO, as we all know that we term chromosomes as particles in PSO. It's like analogous to each other. So here the particle is basically a CVSS pattern. Just like in GA, the chromosome is a CVSS pattern. So here the particle best fitness is basically initial particle best fitness score, which is a CVSS scores. And then this particle velocity, which stores initial particle velocity values. This particle velocity basically measures how far is the particle's fitness score from the best score. It basically calculates the difference between the two. Here the best score we have kept it as 2.0. Here global best value keeps track of the best fitness score of the entire population of particles. Initially we set it to 10, but through the iterations, as the iterations pass, the value keeps changing. Here we are also taken a range of particle velocity, which is between 0 to 8. 0 being the minimum value that it can take, 8 being the maximum value. It's because the CVSS pattern has 8 vector fields, and the maximum number of different values for vector fields between two CVSS pattern can be 8, since there are 8 vector fields. Hence we took this range. Now let's talk about the statistical results of our approach. This table shows various percentage instances for CVSS vectors produced by GA and PSO for different score ranges in 100 runs. The columns show different score ranges, and the value in each cell represents the percentage of the CVSS patterns that fall into that category of score ranges. For example, GA produced 3.5% of CVSS vector patterns, which had score 2.0 in all of its 100 runs, as entirety. If you observe, the values are more or less similar to PSO. A possible explanation could be that the number of vector fields like AV, AC and stuff for CVSS is limited to 8. Hence, not too many options for the GA or PSO to select from. Therefore, both algorithms converge to the same values quickly because the search space is very small. This is a kind of a case study from the Mitre website. This table shows all the CVEs that belong to this pattern that was generated by GA and PSO, which has score 2.1, and we found out all these CV IDs belong to this CVSS pattern. This is the conclusion where I'll sum up everything. So this paper introduced the concept of vulnerability coverage as a criterion for security and vulnerability testing, and we utilize CVSS as a fitness metric for that. It still needs some major improvements, like we are yet to explore more features to be incorporated into CVSS and NVD, including temporal and environmental, and it also needs more tool support and further empirical studies to search the NVD database. With this, I conclude my poster. Thank you everyone. If you have any questions, kindly post them below. I'll be happy to answer them.